Hi, my name is Jake Ponce, and today I will be briefly going over the 2009 stock assessment update on the Arrowtooth flounder. The stock assessment was conducted by the North Pacific Fishery Management Council, and I'll be looking for any ecological recommendations to improve the management of this fishery. In case you do not know what the Arrowtooth flounder looks like, I provided a few pictures here documented by Washington Department of Fish and Wildlife and NOAA Fisheries. As you can see, they are not the most elegant looking fish and are not targeted specifically for recreational purposes yet, as I will explain later. The distribution of the Arrowtooth flounder consists of a wide range along the coast of North America, from central California to the Bering Sea and Alaska. This assessment discusses populations residing between the Aleutian Islands to the East Bering Sea, which hosts the largest populations. The Arrowtooth flounder primarily spawn in deep waters or shelf waters and stay there until roughly age 4 before migrating to slope or shallower waters. However, due to a survey conducted by the US and Japan in 1982, indicating that once they reach around age 9, they seem to migrate back to shelf waters, possibly due to better spawning conditions. As juveniles in the Bering Sea, these flounders have been noted to stage around the deep shelves until favorable conditions arise for them to migrate elsewhere. Over many years of catch data from onboard observers, bycatch data from fishermen, and independent fishery surveys have noted that the maximum length can be found around 80 centimeters with an age span of 25 years. Results in this assessment indicate an average length of between 30 and 40 centimeters, with males being sexually mature at 46 centimeters and females at 42.2 centimeters. Recruitment is estimated to be at 2 years of age at around 25 centimeters. The Arrowtooth flounder is not a sought-after species for harvest due to the mussels degrading rapidly when heated, creating fillets that are of bad quality and little value. Due to new innovations, several methods have been created that neutralize these enzymes that cause the flesh to degrade, such as chilling near zero or immediately processing and freezing. Most fillets for today's markets are sold in Asian markets, used for sashimi sushi or used to make surimi. This info was located from the 2015 stock assessment. Also, I wanted to mention that during trawl fisheries prior to 1992, the Arrowtooth flounder and the Kamchatka flounder were not consistently separated during counts because of the difficulty in identifying the different species due to many similarities. There is a multitude of bottom trawl gear selection, and from what was indicated during the independent fishery surveys were two types: mud sweep ground gear and bobbin roller gear setups. Depths of deployment of the gear range from 200 meters up to 1,200 meters. Of the 2009 catch data, 88% of the Arrowtooth flounder were obtained from bottom trawling, 6% by pelagic trawling, and 6% by hook and line angling. Prior to the 1970s, catch data was combined with the Greenland turbot, which is another important commercial flatfish species. Over 25 plus years of data represented by this figure, showing a general increase of catch of Arrowtooth flounder. Note that the figure also accounts for Kamchatka flounder as well. In terms of biomass, since 1982, Arrowtooth flounder have increased dramatically with landings of 570,600 tons in 1994 and peaked in 2005 at 757,685 tons. The need for continued observation, I think, is necessary due to the worldwide demand of seafood, and the Arrowtooth flounder could be a good substitution. This assessment model is looking at population estimates given catch data weights and lengths to forecast for allowable biological catch and other parameters. AD Model Builder software was used in calculating all likelihood outcomes. Other input parameters that were analyzed is catchability, fishing mortality, natural mortality, selectivity, and sex-specific ratios. Also included were errors and uncertainties, such as the selectivity of the data was opportunistic, making fishery estimates unreliable is one example. Secondly, due to differential migration patterns for male and females, there is an uncertainty within spatial separation and are less available to the catch data during fishing operations, and also some ecological indices as well. This assessment is regulated under Tier 3 within Amendment 56 and follows the requirements of the National Environmental Protection Act, or NEPA, and the Magnuson-Stevens Fishery Conservation and Management Act. With these guidelines, this assessment looked at 7 projections or scenarios to maximize the ABC level and overfishing limit. These projections were run 1,000 times each. The ABC was set at 156,280 tons, and the overfishing limit set at 190,800 tons. Noted within the assessment, the biological reference points consisted of allowable biological catch, ABC, OFL, fishing mortality, and natural mortality. Fishing mortality was set at 40%, and natural mortality was set at 0.2 because of similar flatfish estimates used by Okada et al. In 1980. Furthermore, catchability, selectivity, and sex ratios were incorporated into the model results. Ecosystem interactions were evaluated in this assessment from incorporating bottom water temperature to predator-prey parameters such as seen here in figure 6.19. This figure is a quick overview of adult arrowtooth flounder diet, with juvenile and adult walleye pollock comprising a majority of their food consumptions. The authors did evaluate trophic interactions and noted top predator diets consisting of arrowtooth consumption, such as Pacific cod at 2%, walleye pollock at 3%, and sleeper sharks at 12%, being their top 3 predators. However, of these 3 species, if changes in arrowtooth populations were to decrease, there would not be a large effect in these predators. Also briefly mentioned was how if habitat conditions were to change, such as warmer bottom temperatures with reduced ice cover, that juvenile survival could possibly be increased. The authors included food web interactions within the assessment based on predator-prey relationships and trophic structure of the entire ecosystem. Figure 6.22 shown here shows a prediction of decreasing arrowtooth survival by 10% and letting the other species shown here adjust for 30 years. No significant difference between species except for the flathead sole at a 3% increase was hypothesized due to competition factors between flathead and arrowtooth flounder. This assessment mentions a few recommendations or improvements. First, being able to have a more accurate age profile for arrowtooth flounder would be ideal, as otoliths were sampled but were infrequently aged due to other high priority species. Secondly, the authors mentioned the possible inaccuracy of the catchability and sampling of area swept technique, comparing it to a study by Somerton and Monroe in 2011, as the results of 7 other flatfishes resulted in overestimation. Overestimation, though, was not a concern for arrowtooth due to their lack of attention and fishing pressure. My recommendation would be to seek better sampling techniques to increase the catchability coefficient. The first 2 examples here were more of uncertainties mentioned, and with otoliths being collected routinely but not aged due to high priority species, most of the otoliths have not been aged. By aging more fish, I think the accuracy of the recruitment for the arrowtooth flounder will increase and provide valuable data in the future. Also mentioned was the accuracy of catching the fish was poor due to herding techniques were uncertain. Maybe including more independent studies in the future will progress these data sets. Lastly, the food models, as discussed earlier, were recommended to be rerun due to the data was obtained from the 1990s. My recommendations for this assessment would be to involve Pacific decadal oscillations to the models to see if long-term oceanic conditions have or will affect this fishery. Also, a more extensive data collection that I think would bring value to the stock would be to obtain microchemistry data to have a better understanding of the 2 stocks of arrowtooth flounder in the Aleutian Islands and Bering Sea. In addition, modeling for an intrinsic growth rate would have a great input for fishery managers' decisions in the future. In summary, the arrowtooth flounder is not a specifically targeted fishery and is mostly caught in bycatch. They are not overfished based on this assessment and is forecasted to not be overfished in the upcoming few years. Continuing to analyze CPUE data, I think, is important and can play a key role in balancing other fisheries out. With new techniques for harvesting and table fare, monitoring this species will be crucial. Thank you.